Okay, I visited Rimini many times and happy to be here once more. Now, to begin with, I would say that last time I'm beginning to think perhaps came time to write something about my mathematical autobiography and several words about it. But even a reason I came here, no, you see that it is not that simple for me to come. I prefer to stay at home now, but the results of work of the last year, we are working and very successfully with oral Serra. And the results of this work are pushing me, nevertheless, to talk about it and transfer some message. We think that we promote new motions, new methods, and hopefully we'll have new results, and that's why it's worth to talk about it. Now, we are working in a field of additive number theory. Now, what is it, additive number theory? To say it in one word, I would say so. We have a set A. We ask what A plus A is. No, case around with plenty of things. What is it inverse additive number theory? Given A plus A, what can be said about A? Now, perhaps already more than 16 years, when this word was put in by me, a bit about story, because today and yesterday several people asked me how it appeared. I may explain. First several years of my studies and work in additive number theory, I was on my usual way. And after several partial results, I was heavily involved in worrying problem, trying to diminish number of summands. You remember, Gn, it is n log n, but hypothesis that it is n. And I worked hardly during a year. Nothing came from it. You know, the problem is still opened. And so I was exhausted, and I felt that I can do nothing to get all numbers represented as it is in a Waring problem. Always number of summands and sums were small. And in additive number theory, we want to obtain number of sums which is big. Let's say Goldbach problem. Primes, we want to obtain all evens. And so once I was sitting in a rather picturesque atmosphere and asked myself, we want number of sums to be big. We cannot achieve this task. So what is going on when number of sums is small? Can we say something about it? And this was beginning of inverse additive number theory. I immediately found a first theorem. A with k elements is given. What is minimum? 2k minus 1. When? Only when A is arithmetic progression. This is, I would say, central result of our activity. By the way, it is trivial, entirely trivial. It could be found 200 years before, 300 years before, and simply by some youth interested in mathematics. Nevertheless, it was the beginning of inverse additive number theory. About history. My first student work theme was proposed by my teacher, Alexander Gelfond. And we talk about Waring problem with different exponents. Solution, this set is diverging, and if we suppose that this set is diverging, then positive solution. And this is direct. The fact that this set is diverging is a necessary condition to problem to be solved. And this is kind of inverse question. About next, my paper. Here I want to stress that inverse problem of additive number theory may be of different nature. Not only things we'll speak today, but from different parts of number theory. For example, here we were speaking about Hardy Littlewood function Pn, but if as a base we'll take not all integers, but some sequence of such numbers, we'll have a asymptotic formula of representations. Inverse question is, asymptotic formula is given, what is the sequence? And now we can go to our main theme. Part 1 is simplest result when doubling of A gives not much, only 3k minus 4 elements. Then maximum element here is small, and we can give precise structure. Part 2, Freiman-Ruzsa theorem, when, no, this is known, say. Now, to obtain this theorem, we need some notions, notion of homomorphism and isomorphism, but not exactly in a general sense. Term was Freiman isomorphism or homomorphism. And it is when we have a map from A to B, say 1-1 map, homomorphism. Two equal sums go to equal 1. I am not a cause of this. So, two equal sums go to equal ones. If only two equal sums go to equal one, and different sums go to different, it is homomorphism. When we have this notion, it appeared very, very useful that we can connect sets of different dimensions, which was not existing before. Element of integers may be isomorphically put somewhere in Zn. And then notion of volume came. If we take some isomorphic image of our set, such that now exists some hyperplane in which this set in and degree of a space is maximal, then we can introduce volume, convex hull of our set, for me, where volume is for all isomorphic sets is minimal. So we have a volume. Freiman-Ruzsa theorem was if doubling is not large, Ck, K is number of elements in K, then volume over volume is less than C prime of K. C prime depend on C. This theorem appeared to be useful, but progress depends on connection between C and C prime. And so a long sequence of papers appeared to find in nature this connection. By the way, in my first very awkward exposition, there was only a fact that such connection exists, but real functions, real estimates were found by many people. First of them was Bilo, then Ruzsa, Mei-Chu Chang, Konyakin, Sanders, Schoen. Better and better. The C is less, result is more strong. So I gave a list. I told already about all these things, and this is list of authors who improved estimates in Freiman-Ruzsa theorem. Now, all this, you saw a table. It is part 1 and part 2, and it is past. Now, I'll tell a bit about present a bit later, and want to go to main. And to main part of my talk. There is a progress. And you see, all these proofs of Freiman-Ruzsa theorem were using volume, were using the set in some multidimensional space, Zn. And it is not that simple to work with this volume. You'll agree with me that if we will take something which is not in a Zn, but on a line Z1, this object is simple, something in a segment. It is simple. So our main progress is that we can get rid of multidimensional sets and be happy only with one-dimensional sets. And all future problems of investigation connected with small doublings, with additive combinatorics, may be solved, investigated and solved on a line. Proof, there is, by the way, some version of it in Arxiv. But all these things is now results of our joint work with Oriel Serra. We are, thanks to means of 21st century, we are connected by Skype every day last year, and it helps. So, what we are speaking about? So, we have a set of k elements, and t doubling is given. And what is maximum of a volume? It appeared to be useful to express doubling t with the help of two parameters, and it appeared to be really very useful, because only then we could express our conjecture. Partly there are proofs of some special cases which are rather important too. So this is conjecture of a volume on a line, length of a segment. So this is our aim. I understand. It's a pity. But I'll try to be okay. So, this conjecture to deal with this conjecture, it was important to go to dimension 1. And Then first steps of this conjecture were checked. It is okay, of course, for 3k minus 4, but, and it is a good achievement, we have a proof, a theorem, when this conjecture is okay for 4k minus 8. It seems small step forward, but already this is very important. There is a vast literature about sums for primes, about Kneser theorem for sequences, and the result for 4 gives way to promote these questions substantially. But now main tool which was used everywhere, and I told about it already. All the time we were dealing with multi-dimensional sets. We want to get rid of it. We want to work with one-dimensional sets. And here is the theorem. If we have d-dimensional set of cardinality k and doubling t, then this two-dimensional, multi-dimensional set may be sent by some map which is injective homomorphism in such a way that it is set A is sent to B. And so doubling of B is smaller than doubling of TA. But volume of B is larger than volume of A. It is extremely important. You remember that all our history we were interested in volumes. Now we have estimate obtaining volume which is bigger all volumes existing, and it is one-dimensional. So now we began to work with one-dimensional volumes. We produced, I skipped it already, some parameterization I mentioned. But to work with one-dimensional volumes, it appeared possible to find rather simple formula to work with one-dimensional volumes. And we have to work in this direction, and everyone is invited. We covered part 3 of, say it is a future. Present. Present is that Freiman-Ruzsa theorem found applications in groups. Small doublings in groups give a structure. And development we have into when doubling is almost exact, as in 3k minus 4 case. And several last years, many people, our group, 3 number theorists, I, Stancescu, and Alain Plagne, in this group. But even more important, 4 pure number group theorists are taking part. It is Mai and Longobardi from Italy, Robinson from United States, somebody else.
Marseille Herzog.
Herzog, of course. You heard his lecture. I'm finishing, really.
1 minute.
1 minute, yeah. So there are already not bad results, 6 papers, and it is only beginning to go to a big values of doubling. Now, to present, of course, enormous work of Tao, Green, and others I could not mention. And Last Hope, part 6, when one-dimensional results for abelian case will be developed, we also can go to non-abelian groups. It is 6 part. Thank you.